Good morning to all of you. This is lecture number 10. In this lecture, we will discuss about laminar to turbulent transition flow in a heat transfer. The laminar and turbulent flow is very important in fluid mechanics and in heat and mass transfer. So, when a flat plate is placed in a vertical column and a hot air or a hot fluid which is flowing over a flat plate, there are three zones are developed known as laminar zone, turbulent zone, and transition zone. On the basis of Reynolds number, we can classify these three zones. In case of heat transfer, if the Reynolds number is less than 2000, the flow is laminar. When the Reynolds number is greater than 4000, the flow is turbulent, and when the Reynolds number lies between 2000 and 4000, the flow is transition flow. But in case of a vertical flat plate, we use another dimensionless number which is known as Rayleigh number. So, if the value of Rayleigh number less than 10 to the power 9, the flow is laminar flow, and when the Rayleigh value is greater than 10 to the power 9, the flow is turbulent flow. So, the Rayleigh number is very important in case of a free convection, and Rayleigh number is a function of Grashof number and Prandtl number. So, this is a flat plate which is fixed in their position, and a flow which is flowing over a flat plate. Two layers are developed. The first layer is known as laminar zone, and the second layer is known as turbulent zone. Just as for forced convection, a boundary layer will form for free convection. The boundary layer, which acts as a thermal resistance, will be relatively thin towards the leading edge of the surface, resulting in a relative high convection coefficient. At a Rayleigh number of about 10 to the power 9, the flow over a flat plate will become transition and finally becomes turbulent, as shown in the figure. The increased turbulences inside the boundary layer will enhance heat transfer, leading to relative heat convection coefficient because of a better mixing. The next is a velocity distribution in case of free convection. This is a velocity distribution at a fixed point of the flat plate. The velocity is 0, or we can say there is a no slip condition, and the velocity is maximum at the midpoint and minimum at the boundary. So this boundary layer, this velocity distribution is different from the velocity distribution which is developed in case of forced convection. In case of forced convection, the velocity is maximum at the boundary but minimum at the plate. But in this case, the velocity is maximum at the mid of the boundary concept and 0 at the plate and as well as the boundary layer. So in the previous discussion of free stream velocity, set up the condition for a convective heat transfer. Due to friction with the surface, the flow must be maintained by a fan or a pump, that it is called forced convection. An alternate situation occurs when a flow moves naturally due to buoyancy force. So this is done due to buoyancy force. This is called natural convection or free convection. In case of natural convection, the Rayleigh number is very important and Grashof number is very important. But in case of forced convection, forcefully we can develop two layers, that is known as thermal boundary layer and hydrodynamic boundary layers. So in that case, T infinite is the temperature of the surrounding air, G is the gravitational force, rho infinite is the density of the fluid, Ts is the surface temperature, and T infinite is the temperature of the surrounding surface. So in always Ts is greater than T infinite. Next is free convection boundary layer development on a hot plate. So this is a temperature distribution, this is velocity distribution. The temperature is maximum at the surface of the plate, but the velocity is 0 at the surface of the plate, where delta is equal to the thickness of boundary layer in case of fluid mechanics, but delta T is equal to known as the thickness of thermal boundary layer. So this layer is this distribution is temperature distribution, this distribution is velocity distribution. In both the cases it is parabolic in nature. So this curve in parabolic in nature and this curve also in parabolic in nature. So ascending flow with the minimum velocity occurring in the boundary layer and 0 at the both surface at outer edge. So generally the two types of boundary layer that is known as force hydrodynamic boundary layer and thermal boundary layer, Nusselt number play a very important role. So this figure shows a free convection boundary layer formed on a vertical plate when it is heated. Here the velocity profile is different from that of the forced convection boundary layer. At the surface wall the velocity is 0. It increases to some maximum value and then decreases to 0 again at the edge of the boundary, since the free stream is at rest. Initially the boundary layer is laminar in character and some distance from the bottom edge it becomes turbulent. This one set of turbulent depends on the fluid properties and the temperature difference, that is Ts minus T infinite. So it has been observed that during the heat transfer from a heated surface to the surrounding fluids, the fluid adjacent to the surface gets heated due to the buoyancy force. So buoyancy force also play a very important role. Next is transition to turbulence. Transition in a free convection boundary layer depends on the relative magnitude of the buoyancy and viscous force in the fluid. It is customary to correlate its occurrence in the right to Rayleigh number. So Rayleigh number is the product of Bischoff number and Prandtl number, and mathematically Rayleigh number is equal to G multiplied by beta multiplied by Ts minus T infinite x cube divided by nu alpha, or it is equal to 10 to the power 9. So in case of transition flow the Rayleigh number is equal to 10 to the power 9, but in case of laminar flow Rayleigh number is less than 10 to the power 9, and in case of turbulent flow the value of Rayleigh number is always greater than 10 to the power 9. So there are several mathematical expressions to calculate the Rayleigh number. A transition flow from laminar to turbulent in both force and free convection is caused by thermally and hydrodynamics stabilities. It is observed that the transition in the free convection boundary layer when the value of Rayleigh number approaches 10 to the power 9. The analysis of turbulent free convection is very complex. However, the results obtained from the various experiments have been used to obtain the empirical correlations. So Nusselt number is equal to Prandtl number, Nusselt number is equal to mu Cp divided by K. So there are different types of cases, vertical plates, vertical cylinders. So there are so many mathematical expressions. Number. These are the empirical formulas for flat plate. All condition Nusselt number is equal to 0.825 plus 0.387 multiplied by Rayleigh number whole power 1 by 6 whole divided by 1 plus 0.492 divided by PR whole power 9 by 16 whole power 4 by 9 to the whole square. So this is a mathematical expression to calculate the Nusselt number for laminar flow. Rayleigh number less than 10 to the power 9. For more accurate for laminar flow, the Rayleigh number is given by this equation, second equation. So for this case the Rayleigh number is equal to 10 to the power 9, less than 10 to the power 9. So these are the mathematical expression. Thank you. In this lecture we will discuss about, in this lecture we have discussed, we have covered the mathematical correlations for free convection for a vertical flat plate. In next lecture we will discuss about the correlations for vertical cylinders in case of free convection. Thank you.